Hello and welcome everyone. In this vlog, I will talk about how to build an AI damage inspector using LLaVA, which is a visual language model that can be used to look at the package damage and for the damages which could be there on the package, and then tag this package with the severity of whether it's a minor damage or a severe damage, and also describe in detail what the package looks like. This is very useful for a lot of e-commerce companies, where they might be getting packages in thousands or millions per day, and they would need a system that could scale automatically before shipping the package, because shipping a damaged package could cause a severe money for them, right? So that is what we are going to do, and we will use AI to look at the package and assess for the damage, right? Specifically, we are going to use uh, a LLaVA. A LLaVA is nothing but a vision language model, and it has both understanding of text as well as visual aspects. And that is done by using a projection layer from the Vicuna language model, where we can give an image as an input and ask a question about that image. Hey, what is inside the image? What the person is doing with the image, and things like that. Now, out of the box, the language model, as you can see, doesn't do a great job. So we also need to fine tune the model. Now, these models are typically pretty big. Like, for example, Lava size is about 7 billion. So training on as it is, you will need a very powerful GPU. So that's where we will examine some of the more efficient techniques. First of all, we'll download a data set on which you're going to find in the model with respect to damages. So we will download a model from the Kaggle, which has those labeled images where they are damaged or intact, and we will use that data set to fine tune our model. But even for fine tuning, we are not going to use out of the box because that model is very huge. So we will use a more efficient techniques using quantized LoRa, where quantized is basically we are going to reduce the precision of the model to a 4-bit precision. And we're also going to use a LoRa, where we will not train all the parameters of the model, but we are going to train only certain parameters of the model. It's about 0.13% of the model. And that also will train in such a way that we will run the trained parameters also we will maintain as a combination of two low rank matrices so that storage doesn't explode, right? So typically, instead of storing a single huge matrix of weights, we will store basically two matrices with a low rank, and that way the size of the model gets reduced. So we'll use this technique to train our model efficiently. And I'm going to use a Colab Pro to show you how we're going to do. So before we go to Colab Pro, there are a few things that we need to do. You need to have access to, of course, Colab Pro subscription, where you have access to GPU like A100. That will be using this in example. You also need to have a account with Hugging Face, because that's where we will use, that's the library that we use to download our base models. We'll also use bits and bytes, where that is a library which is required for quantizing our models. Then we'll use a parameter efficient fine-tuned model for training the LoRa. Again, this is available on uh, uh, Colab. We'll also use Kaggle from where we can download our datasets. Okay, so let's look at our code. All right, let's jump to the code. I'm going to increase the zoom a little bit so that you can see the code clearly. All right, that's good enough. So we'll start with installing some prerequisites, which is basically we will install transformers, bits and bytes, and accelerate, which is used for training the our models. Then we'll also install the dataset library. We'll also install Kaggle for downloading datasets, and we'll also use weights and biases. Weights and biases is important if you want to upload the parameters and how your training is doing during the training loss and validation loss is doing during the training. So weights and biases will install. Again, everything is other than Colab is free to access. So you can just go ahead and create your account on Hugging Face and weights and biases if you haven't done it already. Okay, so let's install the prerequisites. So I'm installing the prerequisites now. Don't worry about Streamlit. We're not going to use Streamlit in this particular example. Okay, so all the prerequisites are installed. Okay, now let's go ahead and log in into weights and biases programmatically. And at this point, it's going to prompt us for API key. So I'm going to log in first to weights and biases. Website, and then log in. Okay, then I'm going to click on the profile and click on the API key, and I'm going to copy it by clicking on this button. So API key is copied, and once I execute this cell, it will ask me to prompt it. Okay, it is asking me to enter the API key. I'm going to paste it here. Okay, API key is done, right? One more thing I forgot to tell you is you also need to enter the Hugging Face token here to download your models, and that you can do by going to the Hugging Face site, sign up for the account if you haven't done it already, and then go to Access Tokens. It's asking me to log in, and then you can just create a new token and then use that token to again what you do is go to this key creator setting called HF token and paste your keys here, and then Google will automatically use it that key with downloading the model from the category. Okay, let's continue now. Let's prepare the data set. So before preparing the data set, we just need to make sure we also authenticate with Kaggle, because from there, from where we are going to download the key. Again, basically what you can do is you can go to the Kaggle.com. Again, it's free to use. You can create an account. Once you create an account, okay, so you basically go here. Uh, you create a new token. And once you create the new token, what it will do is it will download this kaggle.json key on your machine and you can start using it. Okay. All right. And so this is a little bit of code where you can authenticate with Kaggle. Uh, and if there's a kaggle.json, I have already uploaded the file and it exists in this folder over here. Okay, that is expired. So let's see, it might ask us to upload the kaggle.json file again. And then we upload it and authenticate it, and then we can start continuing and allow us to download the dataset. So let's see what happens. So I'm running this code. So the Kaggle.json file is not there. So what I'm going to do is I'm going to choose Kaggle.json file from your machine. This is the one. I'm going to upload it, see if it works. So it's uploaded. Now it's going to create a set sample data folder where we will download data set. So if it already exists, it's going to clean it up. So there is no such folder. So we are also going to make a separate key where we can put the Kaggle.json file so that it can start authenticating. And we're also going to change the permission on the file so that we can give an execute permission. Okay. So now we are ready to download the dataset. So the dataset is available here thanks to this user called Rahul M7323, where you have the dataset of all the packages which are labeled as damaged or intact depending on the condition of the package, and each package is a label image and a label associated with it. So let's download that dataset and it's going to unzip it on my content folders locally on my Colab environment. So if you look at it, so it's a download the data here and it has unzipped into this folder. It has two folder, one for the damage, which has the images of all the damaged images, and there's the intact folder with the intact of all the images. We'll look at some sample images shortly. Okay, so then what we're going to do is we are going to create a data frame, right? Wherein we have two columns. One that is an image itself, image path, and the second one is the label. So let's do that. So here is how the image looks like. So here is how the image does it looks like. So we have one column that contains path and the other column that contains status, whether it's intact or damage, right? So let's look at the volume of the dataset, and we will also split it into training and validation. So there are about 628 images. We will train 80% of that as train and 20% of that as validation. So now what we're going to do is this data set just has the images and the columns which says intact and damaged. We also can use LLaVA model to generate a pseudo label wherein uh, we can give some description of the image to the model so that the model can be fine-tuned better. So we will first generate the pseudo label, a kind of a description of the image so that model can be fine-tuned better, right? So what we will do is we will download the base model, which is already available in the Hugging Face LLaVA model, and we will ask the model to describe the image and see so that the model can be fine-tuned better, right? So the model itself first can analyze the image, the base model, and it will describe how the damage looks like, whether it's a minor, severe, and then we will use that, we will append this description of the model as one column in the training data set, and then we will use that data set to fine-tune the same model. Okay, so let's load the model. And now this is using GPU because it's a very 7 billion model with the version 1.5. This process will take some time. It's all loading all the parameters and all the configuration of the model. Okay, the model has been loaded. Now what we'll do is we have created a prompt template for the model where we are asking the model to analyze the image and asking it to generate a pseudo label regarding the damage for the model, right? So let's have this prompt template. And then this is a helper function that we have written because the model generates very verbose output. It's a huge JSON that contains a response from the user as well as a response from the model itself. So this is a helper function that we have written, which can take the model output and just give us the text that you describe that has the damage from the model itself. So this is a little bit of a helper function to do that. So now this is a function that we are calling to generate the label. Basically, it takes an image as an input, uh, image path as an input. Then it actually opens up the binary of the image. It loads this image. Then we are going to pass a user message with the prompt that we have described to the model. And the pipe is actually invoking the model inside and generate the model output. Then we'll use the extract assistant function to extract what the model thinks about the damage on this image, right? And we'll get the output. And then we'll also have a helper function to display the image and the label just to see how whether the model is doing its job or not. And it's simply using the label that the model has generated, and we are going to use uh, a plotting library, which is basically matplot library to plot this. Okay, and we will see how for the few images, probably we'll take a random image and see how the model thinks the output should be. Okay. So this is an example where this is the package and the model. This is the model. The output is generated. The package shows a box of zicuminol C tablets, and there are no visible damage to the box. Right. So we can also try to see uh, another image because this picks up an image randomly and see if it can show you one of the damage boxes. This also there is no damage. Maybe we can try one more. Okay, this is an example where there is some damage, where as you can see, the tin box has some dent, and the model clearly says the model has some dent in it, and it's got some level of damage, right? So the model itself will generate a label, and which can help us to fine tune the model further. So now we know that the model is generating good pseudo label, which can be further used to fine tune the same model, and that can indicate the severity of the damage, right? That's what we're going to fine tune for. So having done this, we have done it only for one image. So let's generate the label text for all the images. So now this is going to take some time because this particular piece of code is reiterating through each and every train image. For each and every image, it's going to call the model. It's going to generate the model, is going to generate the label of it, and then we will append this description itself to the one of the training features for the model so that we can fine tune the model better. Right? So this is going to take some time. I will fast forward the video so that we can come back to it. All right. So now we have pre-processed all the images and have created a pseudo label with a detailed description about the damage. And let's write that file to a local file so you can take a look at it later. Now let's see how data set looks like by printing a couple of records. So now as you can see, the label shows, pseudo label shows a good amount of description with a description about the damage and all. And then we're going to append to that uh, data. So we are going to create a new data set where the input will be this image, the prompt template, and then we are going to create the response from the pseudo label, right? So this is how we are going to use the data set with the pseudo label to for fine tuning the model. So let's create the data set. Uh, this is just reinstalling the bits and bytes packages. Now we will prepare the model for training, right? So let's load the base model first. And we are going to use the QLoRA for quantization, right? So we are going to load the QLoRA via a bits and bytes package. So that helps us to quantize the model into 4 bits, right? And we are going to condition our model to use this 4-bit quantization so that it can run on this A100 GPU, which has about 40 gig of RAM. Without this quantization, the model may run out of memory. So that's why we are going to quantize the model first. Okay, the quantization model is ready. In addition to that, we are also going to use parameter efficient fine-tune package called PEFT to get the LoRa config, wherein we are not going to train for all the layers of the model. We are going to target only few layers like Q PROJ, V PROJ, K PROJ, and O PROJ layer, which are like target layers usually when they are targeted when you're using a LoRa. Uh, and then we're going to also use a dropout of 0.05 so that the model doesn't overfit. And we are going to say tell to the model using this config, hey, we are just going to fine tune only the few layers of you using this LoRa so that we can train it quickly. So overall, we are going to say although there are about 9.5 million models that the model has, we are going to train only the 130, sorry, the model has 7 billion parameters, right? Because it's a 7 billion model. But we are going to train only 9.5 million parameters, which is about 0.13% of the overall model, right? So that we don't want to do a little bit of fine tuning. We don't want to train the entire model. So this is called a fine tuning using only specific layers. So now let's prepare the model for LoRa. Uh, we are going to use a transformer trainer package for training, for fine tuning the model. We also need to use a data collator. Basically, that takes image, prompt, and response. There are three inputs, and then convert into a single model. Because typically, big models like vision language model or large language models, they only take one input. So we need to concatenate them and use that as one input, right? And we need to convert them into the token IDs, which are specifically input for the model, right? So this is the we have created a Lava mask collider package, sorry, class itself. This package takes in the messages and the image as an input, and then encodes them into the processor, right? And basically, what it does is it takes in the three inputs, the prompt, user, and concepts, prompt, user, and the image, and it only keeps um, only the response and mask rest of the stuff with the mask tokens, right? That's what you're going to do. So you're going to keep the assistant response because that's what we want our model to learn, and we want to mask rest of the stuff. Okay, that's why you're going to use collator, and then now we will create the instance of the collator, and then we're going to train our fine tune our LoRa model, and these are the parameters that we are going to use: learning rate. Uh, these are all the hyperparameter where how frequently you want to save the model, uh, how many epochs you want to run it for, and we're also going to report our model training loss as it happens to over weights and biases as the model learns. And then this is the trainer configuration that we're going to load into the trainer, and then we're going to train. So let's start the training. Now the model is being trained. Now this again, the training process is pretty time consuming. It can take anywhere between few minutes to several minutes. So as you can see, it has also created a temporary project in weights and biases, and we can see the progress of that on there. So if you just click on that, as the model is training here, we can watch the progress of the model here. Meanwhile, we can also look at the resource usage as the model being uh, running its training. As you can see, the model's memory, GPU RAM is shooting up. That means the model is shooting. The disk usage is also going up, and most of the training is happening on GPU. Right? This shows you the GPU RAM utilization of the model as it trains. And since we are using QLoRA, hopefully the model doesn't run out of the memory over here. The model is just starting up, and GPU initialization typically takes some time. It is just starting up, GPU is starting up, things are getting initialized, and as the model runs, it will start also showing you the training and other losses. It is still loading up. So as you can see, it has started training now, and the first steps is complete. So now we should also see some training loss here. I'm going to refresh this. Okay. So as you can see, the model is training up, and it has plotted the first point. And as the more steps and losses are available, it will continue to plot the graph. So we'll go back and we'll watch this. I will show you for a couple of iterations and then also show you how the model loss is progressing on the weights and biases. Okay, because one more iteration, it's good to see the training loss is going down. Let's see if it's being reflected here. Maybe I should refresh this. So training loss going down is a good thing, which means the model is converging. So as you can see, the training loss is going down, and this will keep updating as and when we have more uh, training loss points available. So at this point, I'm going to fast forward the model, and we'll show you when the model training is done. All right, so the model training is complete now. So we have completed 120 steps. And as you can see, the model loss is progressively is going down. That's a good thing. And let's see, and even in the weights and biases, it's showing our training loss is going down progressively, which is a good thing. That means our model is converging, right? Now, model has been trained. We also want to upload it to Hugging Face so that we can use it even later on in any other application, like a Streamlit or even a Fast API or a React application. Any other application we can use it. So I'm going to upload this fine-tuned model, both the adapter as well as the actual model itself at these locations, so adapter and the model. I'm going to upload it to Hugging Face. And I will show you where the model is getting uploaded. If you go to huggingface.com, click on your profile, so you will see your models are being uploaded. This is my model and this is my adapter, right? So the advantage of that is you can download this model. You don't have to return again. Even if your Colab session gets lost, you can still get access to the model even later on, right? So now we have uploaded the fine-tuned model. We are going to try to evaluate the performance of this model using both base model as well as the fine-tuned model, right? So, so I'm going to load first the base model itself. No, first I'm going to create a helper function where I'm going to give an image and the model generated output, how the model looks like. Okay, this is just a function. Then I'm going to write another helper function which is going to generate the damage report. Just so that it look good. How the it's easy to interpret, and the function in turn calls the model, tokenizes the input, decodes the model, runs the model, gets the output of the fine tune and the base model, and it can again decodes the output and it can display nicely along with an image, right? So let's create this function. Now let's understand. So we will pick up few random images from the damage and the intact packages, and we'll try to evaluate that. So let's first do this on a base model. So the base model is the model without any fine tuning, right? So this is basically the pre-trained Hugging Face model. We haven't find this is without any fine tuning. We're going to evaluate the performance on that first. So what we're going to do is we're going to load the base model and we are going to call this helper. We are going to go through this images directory that we had here, pick up 10 images at random, and for each of this image, we will try to predict the damage assessment. Again, this is the base model. We're going to see how the base model performs before going to the fine-tune model. Okay, so there is some error here, so I'm going to run this here because I think it's looking for this package. Let me go back and run it again. Now it's running the base model first, and it's trying to do the picking the 10 images at random, and it's going to create the show the damage assessment, the base model itself. So we want to see without fine tuning, how does the model work? Okay, so here is the base model evaluation. So it is this is the input image. The model is saying brown card box is missing its lid. It is not really telling the extent of the damage, whether it's a minor, severe, and the description is also very brief. Here's an example on where the base model is not performing that great. It's just saying that it's missing the top lead, but nothing, no assessment of the damage. Similarly, here the model is saying the box is blue with the flight flowers on it, but and there are no visible damages. So this is like a no damage box. Here also, although there are some holes here on this box, as you can see, but the model is detecting that it's no visible damage. Uh, Similarly, here it is saying there is a slight damage. So the base model performance is not that great because the description is not that great. Also, the severity assessment is not there, right? Same thing here, very brief description. Here is example of no damage. Here is an example of no visible damage. Here also there is damage to the box, as you can see with the holes, but the base model is saying there is no damage. So here there are several damages to the box. The boxes are open, they're everywhere, but this is just describing a very simple statement if the model is damaged with some tear. It is not giving me a detailed description of the damage, right? So this is the performance of the base model. Now what we'll do is we will evaluate how our fine-tuned model, which we have specifically tuned for the damages on the boxes. Let's see how that performs. So for that, what I'm going to do is I'm just going to download the model from my Hugging Face where I had uploaded the fine-tuned model. Again, the other code remains same where processor, tokenizer, my processor, we load the fine-tuned model. And then since we use PEFT for fine-tuning, we need to precondition the model on PEFT. And we will evaluate the model again on the same directory of the images. We'll take that 10 images in random and see how the model outputs. Okay. Now now we are evaluating the performance of a fine-tuned model, which we expect that it performs much better than the base model. So now it is started running on each of the images. Let's see how the output would look like. Okay, so now here, as you can see, the model is clearly saying where exactly is the damage. The box is damaged with a tear on the inside, as you can see, and it's also indicating the level of the damage, right? How much the damage is there, and also it is doing a nice distance from the where exactly the damage is, right? So that's a good thing. So let's look at the second image. Now, see, earlier this image was showing no damage, but here seeing the severity is minor. Now here we are seeing there is no damage to the box. Here is an example where there is a detailed description of the damage, right? The damage, for example, here the damage with the broken corner and it's a severe damage because the box is almost no use. Uh, then it also indicates that this box is a fragile. That means the damage is can get worse if you don't handle it carefully, right? And also it says the condition of the damage and all, right? So it gives me a much more description of the damage. Let's look at this. So this model earlier, the base model was showing no damage, but here it's saying there's a small tear inside over here, and it's a moderate level of severity. So here there is an example where there is no damage. Uh, Here is an example where there's no damage. So here also is an example of a box with a little bit of damage over here, and also saying the other things about how the model, how the presentation of the box looks like, which is a pleasant. But overall, as you can see, it is doing a good job. The fine-tuned model is doing a really good job on assessing the detail of the damage, what exactly is the damage. Also, it is telling me the severity of the damage, right? Whether it's a moderate, minor, or severe. Here's another example. There's a no damage. So this is how it shows after fine tuning a model just a little bit, not too many examples. I think we used about 700 samples. As you can see, the performance of the model can be changed significantly, right? Now the model can clearly assess the damage on the packages and the severity of the damage. So that's how you can train any visual language model like LLaVA efficiently using quantization as well as QLoRA to assess the damage on the boxes. What you can do is you can write the exact same code, like you can do this in bulk, like using a Python script, or you can also create a web application using Streamlit or React, right? Any front end of your choice. And this you can load the model using exact same code. Basically, you need to use this code, and you also need to run it on a machine because this needs a GPU. At least A1 unit. As well as you can run on a GPU machine with the Python code based on all the packages. You should be able to run this on any web or scripted environment. Thanks and bye.